Okay, I just wanted to stop the transcription. Okay, before I proceed, do you see the PDF file on your screen that says the sanitation? One of you could please just confirm with me. Anybody? Do you see the PDF file? I have shared that. Hopefully, I've shared the right file. You see it. Okay. Thank you very much for that. The file you see on the screen, this is from the Red Handbook, the CSR planning guidelines. And this is just one chapter extracted from there. And what you see actually is not, or what I've taken out for you is just the relevant pages that you need for this particular module. Right? It's much more extensive with regard to sewer reticulation, but I've just covered the section that you would need. And if you look at it, if you go to it, immediately you'll see it's just the appendix that I've actually included here for you. On the Moodle website, you do have the full Red Handbook for the CSR guidelines. If you want to read the remainder of it, you can actually go through it. The sections that I've omitted, when it comes to sewer reticulation, they are the level of reticulation that's provided may vary. Right? You could have, for example, pit latrines. You could have septic tanks, and then you could have where we have a proper sewer reticulation systems like the one you see, like the ones that you are going to study, right? Where we have waterborne sewage treatment, where basically the waterborne sewage reticulation. In the pit latrine, that's a dry system, and it does where you do not have proper sewage treatment plants or facilities, or there's no water supply, then that's inevitable, and that has to be provided. It does come has its comebacks and things like that, or not comebacks. It does have its drawbacks. Uh, and we all heard about incidents at schools and things of where things have gone horribly wrong with septic tanks. Right? But the guidelines for the construction of the septic tanks, the sizing of the septic tanks, and everything is provided for in the CSR guidelines. But we're not going to be studying it in this module, so I've left it out. In similar way, for example, you do not have a sewer reticulation network. Right, like for example, you may be living in a rural area or somewhere. You may have access to borehole water, uh, but you don't have a sewer reticulation system. There's no sewage treatment plant as such. Right. So in those systems, you might have a waterborne sewer where you utilize what we refer to as septic tanks and soak away pits and things like that. Again, the CSR guidelines provides you with all the information you need to design those kind of systems, but it's not within the scope of this module. We won't have enough time if we were to cover it. And, those septic tanks and soak pits and things are very relevant, and you will come across them from time to time in rural scenarios. They're used in some of our national parks. For example, if you go to the Drakensberg and places like that, some of those national parks, there are no sewer treatment plants as such. Right, so where you do not have a sewer treatment plant, then those facilities are provided. It is a waterborne sewer, but you don't have a sewage treatment plant. Uh, and yeah, you'll find information in the CSR guidelines. I don't want to spend too much time on that. Right. So the one that we're talking of here is waterborne sewage systems, where it all goes to sewage treatment plant. The water is treated, and then the water is then let out into rivers or the sea or somewhere like that. Right. So this is the kind of sewer that we're looking at. Right, so it says that right at the top, these guidelines are applicable to the design and construction of sewage reticulation for undeveloped residential areas, where food share houses are to be provided with full waterborne sanitation. Right, so that's the term I was looking for, the full waterborne sanitation. So that's what we're actually designing, and that's the scope of this particular module. That's what we look at. They do not apply to on-site drainage and do not cover any form of on-site disposable such as septic tanks and soil percolation system. And I just spoke about that just now. Right. Uh, Okay, the actual design of it, to design the sewer reticulation, you know that we're going to have sewer pipelines that we will have to position in the ground. In the last lecture, I spoke about some information I gave you about the considerations that would go into the layout design for the reticulation system. In this lecture, I want to look at the actual considerations that we look at in the design of the pipeline. And obviously, to design a pipeline, you're going to need a peak design flow. Well, that's what you're going to be after, peak design flow. Can I just get my pen out here? Let me just pull out my red pen. Right, so we want to get to this point here where we have the peak design flow. But to get to that point, firstly, we will talk in terms of the flow in the pipeline, and the unit that we will use is liters per second. Right, so that's what we'll be talking in all of these guidelines. It'll be liters and liters per second. That's what we're going to be, the units that we'll be working with. Then the depth of flow and infiltration. This is the depth of flow in the pipe, and infiltration is extra flow that comes into our pipe, that infiltrates into our pipeline. Right now, we're talking of open channel flow in a circular pipe, and I have given you some guidelines for that, some formulas and things that you'll find in this particular note that I've prepared. And you'll see the relevance of this. Just now, I'll explain that to you, right? The relevance of this particular set of notes when it comes to the actual design of the sewer pipelines. So the depth of flow, we first want to work out when we get to the peak flow, right? Uh, this particular paragraph, what it tells you is you're going to design your full flow. So you'll work out uh, what your design flow is, and then you'll multiply it by 15%. You'll add 15% more to that because uh, uh, in a sewer reticulation system, it is common during a storm event. So you'll design your sewer reticulation system, and you'll work out what the maximum flow for that, and you'll size a pipe for that. But it commonly happens that during a storm session, during the storm period, you do get some infiltration of storm water into the sewer reticulation system. We never ever design our sewer reticulation systems to carry storm water. That's an absolute no-no. One would never ever do that. You do not want to contaminate stormwater with sewage. Stormwater has far fewer contaminants in it. It's a cleaner water, uh, so you wouldn't want to contaminate the clean water with sewage water. Sewage water has bacteria and dangerous viruses and various other things in it. So we would never ever mix stormwater and sewage. Yeah, so that's an absolute no-no. But what does happen sometimes, our sewer reticulation system, our pipes, for example, may have joints that may be leaking. We have manholes and at all our bins and changes in levels and things like that. And through the manhole lids or somewhere, sometimes you may get as the rain falls on them, you may get some seepage into those manholes, so you'll get sometimes stormwater coming into your sewer reticulation system from there. You also have in residential units, you have at home and in the houses or even at businesses, what we refer to as gullies, and those gullies are open to the air, and you can get stormwater, for example, during a heavy storm event, where you might get slight flooding occurring in certain areas, and then you can get stormwater entering into your sewer reticulation through the gullies. Sometime during in a storm event, maybe a manhole cover might come off or something, and then it'll be due to flooding or whatever, and you might have stormwater infiltrating into the system. Right. So that's what we allow a 15% factor for that. So that's what this allowance of 15% takes into account. Right. Why I'm delving on this is just to stress the point that by design, we will never ever mix stormwater and sewage. Right. Also, the volume of water of stormwater is much, much larger than the volume of water of sewage that we have in our pipelines. So our sewage pipelines are normally small pipe sizes, maybe 150 around there most of the time, and then towards the end, as we approach the outfall sewer, we might start getting larger pipelines, maybe 200, 250, maybe 300 at most, in our sewage pipe, in our sewer and reticulation network. Stormwater usually starts off at 350 diameter around there, and because of the volume of stormwater, it's much larger than sewage flow. So uh, you would flood your pipelines, and you would also flood the sewage treatment plant. It's not designed to handle the volume of water that comes down with stormwater. That's the other consideration, that at the actual sewage treatment plant, we need to be careful we don't flood that whole system up. And if that gets flooded out, then you're going to get raw sewage flowing into your rivers and into the sea. Okay, so uh, we will design, we'll work out what our the average daily flow rate is. We'll multiply it by a peak factor to get our peak design flow. And when we get the peak design flow, then we will multiply it by a further 15%, so that we'll get to allow for stormwater infiltration. So what's the average daily flow in your the per pipeline of that, right? So if that's the first thing we need to calculate, is what's the average daily flow. Now the average flow, this is the amount of water or the amount of sewage water or foul water. That's the terminology you might find in some books. They refer to it as foul water. So the total volume per dwelling unit per day. Right? So that's why we say average. Right? So we can work out what the average flow is, and then obviously we will then have to apply a peak factor, because we do not uh, output sewage into our reticulation system on a constant average basis throughout the day. Right? There's certain peak periods during which uh, we will use our bathrooms or toilets. Most people shower in the morning or and in the evening before they go to work and after they come to work. So the peak periods will be concentrated during a certain time, and we'll get the peak flow, and we'll have to design for that peak flow. Okay, so the average daily flow, if you look at this, the average daily flow per single family dwelling unit, as you can see, per single family. Notice that that's per single dwelling unit. Right? So that's one home. That would be referred to a dwelling unit. For example, if you're living in a block of flats, then one dwelling unit will be one flat, right? Not the entire building. The building may comprise 25 apartments or 50 apartments, but so each family, right? Each family occupies one dwelling unit over there. So if there are 25 apartments, then it will be 25 dwelling units in that particular block of flats that you may be referring to. Right. So per the dwelling unit in sewer, you see we break it down per income group, right? So you can see here in table C.1, we have the income groups, and we have three income groups: lower, middle, and higher income groups. And the consumption of water uh, for lower income, and this is per dwelling unit, right? Not per person. So notice it's per dwelling unit. 500 liters per dwelling unit for lower income. For middle income, 750, and for higher income, 1,000 liters per dwelling unit per day. So it's per day. You see, it says here daily flows. So it means it's per day. And even if you look at the table, it says liters per dwelling unit per day. Right? So that will be per day. And then you'll see here that it gives you the average number of persons that would be in the dwelling unit. So for lower income, usually you'll find more people staying in the dwelling unit. So you have 7 people. For high income, you're looking at 5 people per dwelling unit. Right? So if you're looking at the average consumption per person, that 500 liters is spread out between 7 people in the lower income. So obviously the consumption is less, and in the higher income, the 1,000 liters is spread out between 5 people over there. So a much larger consumption in the higher income group, right? Because usually in the higher income group, they can afford to use more water, so uh, the sewage outflow would be much larger in a higher income group. Right. So this table one, that's an important table that we have. So let's look at the right. So this is per residential dwelling unit. That's what this table is. Then you also get consumption of. It's not only residential dwelling units that use water. Uh, you also get other sites, for example, schools and business sites that would also uh, use water, and then you'd have sewage outflow from there, and also from church sites and other maybe factories and industries and things like that. Now, when we calculate the peak design flow, the important thing to remember is we will not count the flow from schools or business sites or, for example, church sites, unless we have some exceptional information and we know about how those zones are used or how those properties are used. And the reason behind it is that we're designing for a certain peak flow, right? And that peak will occur early in the morning and in early in the evening, when people are preparing to go to work and when people just return home from work. During those peak periods, there's no one at school or very few people at school, and there's usually no one at the church site. Right? So uh, that's why we do not combine those the flows from those particular areas with the peak flow that we're going to design for. Right. So even in this table here, you see it's just for dwelling units. No information is given about, for example, schools and the size of schools and things like that. There are other guidelines where you can find out the information. So, for example, if you're designing the reticulation with the system within the school, there are SANS codes of practice that you can use to determine, based on the number of pupils and the number of classrooms and various other factors, you'll be able to work out what the flow in a particular school is. Usually, it's actually based on the number of what we refer to as WC pens, or basically the number of toilets that you have in a school. And based on the number of toilets that you have in a school, the peak flow will be worked on that. But for our case over here, we're not going to consider the flow from a school. It's not that we're not saying that there's no flow, but that flow occurs when the residential units have a very low flow at that. So, for example, maybe a school's peak flow will be during the tea break or lunch break, maybe about 9 o'clock or 10 o'clock, and maybe again at about 1 o'clock, which from a residential unit point of view, you'd have very, very low flows occurring during those times. So it would easily be accommodated right within that pipeline. Okay, so we want to move to the peak design flow. The peak factor that we will calculate, the peak factor, that's just to show you that you have your figure C.C1, C.1, and that gives you the peak factor. Right, on the vertical axis, you see the peak factor. On the horizontal axis, you see it's the population served. So this tells you why, for the residential unit in this table, you're given the population per household. Right? For low income, 7, and for high income, 5, because you'll have to work out the number of people you are serving in that particular township, or the number of people you are serving by a particular pipeline before you can work out the peak factor. So that's where we need this the second row in this table over here. Right, so we will then calculate the peak factor from figure C dot 1. Okay, so coming back here, the peak design flow, so that we will have to calculate the peak factor, but we need the average daily flow. The average daily flow will be liters per dwell. If you look at this, the unit here, uh, liters per dwelling unit per day. And that is what we will read up from table C1. Depending how many dwelling units we are serving by a particular pipeline, and depending on the income groups, it may be multiple income groups, so we'll have to just multiply appropriately from here. And we will then get the total liters per dwelling unit per day. And then you'll be dividing it, that's for the full day. So our unit is, I mentioned to you earlier, is liters per second. Right? So liters per second. that's our design units that we'll use. So we then need to convert that to seconds. So 24 hours is in a 24-hour period. In 24 hours, we have 86,400 seconds. So that's why we're dividing it by that 86,400. Right. Right. So that's what we will do to convert that to liters per second. So once we've got that value, uh, so that will be our then our average daily flow. So this will be in liters per second. We then go to calculate the peak flow rate,
Sorry,
which
sir.
means we then have to multiply by our peak factor. Sorry.
May you please go back, sir? I just want to see in the parts where you were talking about the or that A value, sir. So to get that A value, average daily flow, let's say we had two low income houses. So what would be our A value?
Sorry, if you had two low income houses,
Yes, what would be our A value, sir?
1,000 liters.
Oh, okay.
Because
Now
it's
I
it's
understand.
five it's 500 liters per house, right? For low income. So if, for example, if you had one low income and one middle income house, then it will be 500 plus 750. So it will be 1,250 liters per day, like that. That for that A value over there. Right.
Oh, okay. Thank
Okay,
you.
you'll see it in the. I'll go through a tutorial example just now, and then you'll see it coming out in the example, right? So we then, once we've calculated the average daily flow rate, we will then multiply it. You see here, basically the procedure is given to you in this guideline. So you then can calculate the peak flow rate, and that's simply your average daily flow rate multiplied by the peak factor. The peak factor you read off from this table C.1, depending on the population that you would calculate. And so we will then multiply it by peak factor, and then we then add another 15% for stormwater infiltration. That is, now there are certain instances where it's not possible to get stormwater infiltration. They are depending on which area of the network you are actually serving. So if it's not possible to get stormwater infiltration into your network, then you wouldn't design for that. You wouldn't add the 15%, right, for that extraneous source. But for most townships, in most applications, 95% of the applications, there will be stormwater. You will allow for this extraneous flow. So you then take your peak flow rate and you will then multiply it by 15%. Right, so you can see uh, the peak flow rate and then multiplied by 15%, and then you get your design flow rate, which is C over here. So that is the flow rate for which we will design our pipeline. Right. So uh, this is the next paragraph that you see here. This is just the for a population for example, of 1,500, and you're given an example. You can then work out what the flow rate liter per second is over here, and you can go through that exercise and check it, and you'll get that. Right. Uh, then we do not have an attenuation system. Attenuation system is where you have a sump, for example, where you collect and then you then would have a pump or whatever. So you can ignore the paragraph on attenuation systems. The flow formula, you're given the n values, and you'll notice that for our design in this particular module, we'll be using the Manning equation. Right, so that's the equation we will consider. Uh, in the actual design situation, if you want to use some of those other formulas, you also would use it. Some design officers would use those. As you go down, they become more and more accurate. But the Manning equation is good enough because no one actually knows the exact flow rate that's going to occur in a pipeline. Humans are humans. One day you may use a little more water, you may spend a little more time in the shower than the next day. So it is by its very nature an approximate procedure, the design of it. Right. So, but you'll notice just something I want to point out: the the Manning coefficient is given in these guidelines. Now, if you're using a new pipe, you might have a much lower Manning coefficient, but we would not use that because you remember you're designing for maybe a 50-year period, a 50 or 60-year period. And the condition, the internal condition of the pipeline will change as it ages, right? After a few years, you will develop like a slime on the inside of the pipeline. So you actually got to, that will be the surface of the pipeline in a few years' time. So that's why the guidelines is specify to you what N value to use. You'll also notice it's just an N value. It's not telling you what material, whether steel pipe or plastic pipe or earthen pipe, clay pipe, whatever. It's the same Manning coefficient that we're using. And the reasoning behind it is, irrespective of the material of the pipe, you do develop a layer of slime around on the perimeter of the pipe, and that is then the N value. That will determine the N value, which is N equal to 0.012. Right. Uh, your minimum size of the sewers, I mentioned to you in the last lecture. Just remember, the 100 millimeter, we would not use it. No municipality will accept the 100 millimeter. This is for where you're doing internal reticulation within a property. That sometimes you get large residential estates or as such, right, like complexes or gated complexes where you may have 20 dwelling units or 50 dwelling units within that gated complex, and you're designing it within those complexes, then you may use a 100 diameter pipe. But for the municipal reticulation, the municipal system, right, so that's a public system, the minimum diameter would be 150 millimeters. So just remember that. So that's the 150 and you normally see the NB, that means nominal bore, when you refer to a pipe size. The limiting gradients, uh, the idea behind the limiting gradients, gradient simply means slope. So the slope of the pipe of the limitations on the slope of the pipeline, uh, we will limit the slope of the pipeline such that we achieve a minimum velocity of zero point 0.7 meters per second. Right? And then there will also be a maximum flow, and that depends from country to country. So some countries would accept 1.5 or 2 meters per second. The odd one might go to a little bit higher than that. But generally, we restricted by the minimum velocity. Uh, and now, the minimum velocity in sewer reticulation is much more important than the minimum velocity for water reticulation. And the reason behind it is that sewage by its very nature has particles in it. Right, so there would be grit and various other particles in it, and if the velocity is too slow, these particles would tend to settle out. So you need a minimum velocity to push those particles along so that they don't settle. If you get settlement occurring in the pipeline, then you will get a blockage occurring in the pipeline with time. That as the particles settle, the diameter decreases, and then eventually you get a blockage in the pipeline. So the minimum velocity is very important in a sewer reticulation system, and that's what we will always check that we can achieve that. Now, again, different countries and different guidelines, the way this minimum velocity is specified is different. You'll notice the term here, full bore velocity, right? So it's not the actual velocity in the pipeline. Now, why is that? What's this term of full bore velocity? This is if the pipe, when the pipe is running full, right? It's still gravity flow, it's not pressure flow. It's still under gravity flow, but we're assuming when the pipe is full, what will be the velocity then? Now, we have open channel flow in our pipe. Sometimes, and we have a minimum diameter for our pipe. Remember that we have minimum diameters for the pipe. So sometimes in our design situation, even with the peak flow, our pipe might only be flowing quarter full or half full. Right. So if it's like that, if it's not flowing full, then you'll have an actual velocity because your pipe is not flowing full. So if it's less, then the velocity will be different from the full bore velocity. Right. So, for example, if you look at these guidelines, this particular pipe here uh, that you're seeing in this diagram, the hatch section at the bottom, that's the flow in that pipe. So that this particular pipe is only has that much of flow in it, and the rest above it is all air. Right. So it's not a full bore flow. The full bore flow is when the entire pipe is filled up. So from bottom to top, the entire pipe is filled with sewage or water. Then we talk of full bore flow. in our pipelines. So the design guidelines in the South African guidelines, we generally check for full bore flow. In other regions of the world, other the guidelines, they would normally, some not normally, some countries would specify 0.7 meter per second for the actual flow. Right? So the actual flow here will be, for example, this depth D that you have here in this pipeline. So the depth D here, that's the actual flow. But the full D, the capital D, that's the full bore flow in the pipeline. Right? So coming back to these guidelines here, so we then have minimum pipe sizes and the minimum gradients that we have over here. Now, this is, with regard to the full bore flow, there is good reason behind it. If you had to work, set the zero point 0.7 meter per second for the actual flow, usually you'll find in our pipelines, the flow will be actual flow could easily be less than 0.7 meters per second. It might be zero point 0.5 or sometimes zero point 0.4 meters per second, the actual flow. Right? But we will design for full bore velocity. Now, if yes, if it is the actual velocity is slower, you will get some sedimentation occurring. If you get the sedimentation occurring in the pipeline, so the particles now will fall out of the flow, or you get so you get sedimentation occurring. Uh, the pipe diameter decreases, which means you might start to get a little bit of a blockage. But eventually, as the particles settle out of flow, and you're getting this partial blockage building up, eventually the pipe will fill up behind it. Right? You'll get this backup of flow behind the pipe, and the pipe will fill up, and you will reach a stage where you get full bore velocity. Right. And then it will flush out whatever blockage was building up in the pipeline, where you had all this grit and things settling out. So where you had grit settling out from the flowing switch, settling out and settling in the pipeline, you will eventually develop, as a blockage starts to build up, you will eventually get full bore flow conditions, and then it will be fast enough to then carry all that grit away from you. So it will be like a self-cleaning pipeline from that point of view. Okay, so you'll find because of this, to maintain that minimum full bore velocity, the codes will usually specify a minimum grade for the pipeline, and you'll find there are some minimum grades specified over here in table C2, that for different uh, diameters of pipeline. This is just to assist you, so you know what sort of grade line that you're looking at. If you have to work it out, you'll see these are all based on a full bore velocity of 0.7 meters per second. That's what you're trying to achieve, a full bore velocity of 0.7 meters per second. Right. Uh, okay, so once we got our peak, excuse me, my apologies, I just needed to clear my throat. Once we've got our peak flow, let, let me just clear out the clutter here, just to outline here the design procedure. And now I'll go through it with an example now, and you'll see how it all comes together. Right, so uh, once we've determined our peak flow, right, so we're going to determine our peak flow. We'll multiply it by that 15%, everything. So we've got our peak flow. We will then have to select a pipe size. We'll guess our pipe size. We'll then have to check the velocity that we can maintain. So we'll have to look at the gradient that we need in our pipeline. Now, the gradients, because we have gravity flow, there are limitations on the gradient. It depends on the terrain of ground that we have. Right. So if you have a very steep sloping ground, you cannot lay it as flat as you may have liked to lay it. Right, you'll have to lay it at a certain gradient. So there are limitations that come with the gradient. So we will check the gradient flow, the gradient of the pipeline. And again, as we proceed through this particular topic, you'll see that will come into play a lot more when we look at long sections and things like that. Right. So that's why this table also provides us with those with guidelines for that. Now, the guidelines of it, they go on to non-gravity systems. Right. So that the non-gravity would be a pumped pipeline, and you see the word rising mains. that's referring to the pumped land. Again, we're not going to concentrate on this. You can read it up. The information is here. It's available. What I wanted to stress for you over here is the minimum, the maximum velocity that we have in the pipeline. You pick it up from here, 2.5 meters per second. Right? You notice in the earlier section, they only specified the minimum velocity of 0.7 meters per second, but we will also select the grade of our pipeline such that the maximum. Excuse me, my kids are making a racket in the background. I just need to go and tell them to keep quiet. Just give me half a minute. Okay, I'm back online. My apologies for that. You must have heard the racket in the background. My children were playing there. Okay, so I was talking about the velocities. So we would also be careful with regard to a maximum, and normally for sewer reticulation, we set the maximum velocity at 2.5 meters per second. And again, the reason behind having a maximum velocity when it comes to sewer reticulation design is that if you exceed a certain velocity, then the water shoots past uh, the sediment in the flow. So it actually the sediment gets left behind. The water wants to move so fast, the sediment cannot keep up with the flow. Right. So then you get again sediment settling out from the flow, settling into your pipeline, and you can then also get blockages occurring like that, where the sediment actually the shooting water overtakes the flow of the overtakes the grit. The grit cannot keep up with that, and so that's the reason behind having one of the reasons why we would set a maximum velocity. Another reason why we have a maximum velocity is if the grit can manage to keep up with the water, then you'll develop a scouring effect on the pipeline. It's like sandpapering the inside of the pipeline, because now that grit has so much of momentum in it, it would then uh, scour, right, the pipeline. It's like as though the pipeline is getting sandpapered inside, and it would reduce the life of that pipeline. Right. So that's those are some of the reasons why we would limit the speed or the velocity of flow in the pipeline. So maximum of 2.5 meters per second, and I might say 2.5 meters per second is still a high velocity. Right. So ideally, one would try and keep away from that. Usually, in a practical situation, we're talking of between zero point 0.7 to about 1, maybe 1.2 meters per second. In the odd case, like I mentioned, if you have very steep terrain, then you would have to place your pipes at a very steep slope, and then you might end up with those high flows. But it would just be you try and restrict it to maybe just a few pipelines in your network, and not all of them you'll want to flow at. You'd want them to flow at that velocity. Right. The Again, the rest of the content that you come across here refers to now pumped pipelines. So you can within this particular section here, the non-gravity system, you can read through it, but it refers to a pump system. We're talking of gravity flow, so I'm not going to delve further into those systems. The actual design. And you can read up to about the minimum depth in cover. It's important. That's the minimum depth of minimum cover to your pipeline. When you talk of cover, they're talking the cover to the outside of the pipe. Just bear that in mind. Right? So if you have a pipe in the ground like that, and the ground level is somewhere like that, that's your ground level, then they're talking of that distance above the pipeline, the minimum cover to your pipeline over there. So that's what we refer to when we talk of the cover to a pipeline. So it's the amount of soil above the top of the pipe that we're talking. In servitudes, this is where we would not have vehicles, so within the property, and you're not going to get, for example, trucks and cars and all driving over those areas. We'll try and achieve a minimum of 600. If you cannot get 600, then we need to provide some protection above the pipeline. In sidewalks, so you have a road and you have a road with sidewalks, 1.4 meters, because vehicles do drive onto those sidewalks. Right? And in within the road's carriageway, because now you have vehicles, you have trucks and cars and all driving on the road. So there you would have a minimum cover of 1.4 meters. Right? And you can see it's the same for roads and sidewalks. And the reason being that vehicles will drive onto a sidewalk, so you will need the same protection on a sidewalk as for a road. So these are some guidelines. Again, you can read through the rest of this chapter. The diagram below shows you if you cannot achieve this minimum cover that's specified here, if you cannot achieve that minimum cover, then you would then need to provide a concrete slab to provide some protection to that pipeline. And so especially in roads or sidewalks, you would need to provide that level of protection over the pipeline. Read through all of this. It's information that you should know when you go out in industry and you're more involved in the design. You'll come across that. If a particular municipality does allow for curved alignments, in my last lecture, I told you we always lay the pipeline straight. Right? So we don't lay a pipeline curved. What do we mean by that? Curved pipeline? I never actually told you that. So let me just, I'm just going to draw over the writing here. A straight pipeline means you've got a manhole there and you've got a manhole there. And the pipeline, this runs straight between the two. It connects the center lines of those two manholes. So if you got a pipeline, another pipeline there, then these are straight pipelines that we have. A curved pipeline means you're laying the pipeline on a curve. So for a curved pipeline, from the center of the manhole, you're then going to lay the pipeline like that, curved like that, and it's going to go like that. So that's a curved alignment that we talk about. Now, why curved alignments are frowned upon, or why we would generally avoid curved pipelines, is if we get a blockage, for example, on this pipeline here, let's say somewhere here, and it's blocked solid, and it does happen. You can get roots, for example, that will penetrate through the joints in the pipeline and or through a crack in the pipeline. There may be large roots. Eventually, they crack the pipeline and then they enter into the pipeline. And there's a lot of nutrients in a sewer pipeline. So plants, many trees and things, their roots will try and penetrate into the pipeline because they can get nutrients and water. So they would block that solid. If you try to rod it, you will not be able to open it up. If you got a thick root through there, a rod will not push those roots out. They'll stay where they are. So you cannot clean this blockage by rodding. You would then need to dig up the pipeline and physically clear the blockage. Right. Now, if you have, for example, I'm just going to go back and show you over here. If you have a straight pipeline from one manhole to another, it's very easy to locate the point where the blockage occurred. So if the blockage is at some point over there and it's solid, and you now need to dig and break out the pipeline to clear the blockage and add a new pipe segment there, then uh, you know how many rods you're putting in before you encounter resistance. So you will not be able to push past that point there with your rods. So from the length of rods that you put in, you normally join the rods. They come in maybe 1 meter or 1.5 meter or 2 meter lengths, whatever. And it's like it's thick, but it's flexible, the steel rods. Right? So you would then push them in from the manhole and push it down. So you'd know how far down the pipeline the blockage occurs from your rods. And you would also know where this point is because you'll know where this manhole is. You'll know where the second manhole is. You know where your first manhole is. You can tell somebody to stand there with a stick or if you have a survey staff, they would hold a staff at that manhole and at this manhole, and you can physically gauge the straight line. So you would identify this exact spot where you would need to dig. Right. So with straight pipelines, you can do that quite easily. That it can be done. But now, if you have a blockage on a curved pipeline, if somebody is going to stand, uh, if you put a staff at that manhole and a staff for that manhole, you'd only get the line of vision like that. That would be your line of vision. So you wouldn't know. You know how far down the line, but you wouldn't know where to actually dig. Must you dig at that point there? Because you don't know quite the curvature of that. Must you dig at some point there? Must you dig at some point there? Where to actually locate the pipe? So you then have to dig a cross trench like that to first find the pipeline and that. And even then, when you're digging that cross trench, because of the curvature, you don't actually know how far down the pipeline you are. You might actually be digging past the blockage. Maybe the blockage is at that point. Uh, right. So there are all sorts of difficulties come with that with this curved pipelines. So that's why most municipalities would tell you that they do not want curved alignment for your sewage pipelines. Right. And you see there's if you do use curved alignment, it would usually be save. It will be for saving for reducing the number of manholes. Right. Manholes are very expensive structures in a reticulation network. They are probably the most expensive item in your reticulation network. So the if you want to reduce the number of manholes, then the only way you can do that is by using curved alignment. So if the odd municipality does allow you a curved alignment, then there are guidelines provided there with regard to that curved alignment. Okay, the rest of this, I'll come back to manuals in the next lecture, and I'll discuss it in quite a bit of detail, what goes into a manual and how they serve their purpose and what's in the manhole and things. So I'm not going to discuss it now in this lecture for now. I want to move on to is the actual design example where you see this, how you select a pipeline and will calculate those peak flows and things like that. So for that, for the actual example, uh, I'm going to come, I have a tutorial example for you and I'll walk through this with you. Right, so let's say this is the same diagram that you had in those notes, the first set of notes that I went through yesterday, explaining to you about the positioning of these pipelines. Right. So let me see if I can enlarge it. We have a township network over here, a sewer reticulation network. Right. And we have all these pipes that we are proposing to lay in the ground. And for this particular tutorial, let me just go, okay, let me just zoom out a bit. You're given some information about this particular suburb. You're told it's a middle income group. Right, on the right hand side, you see it on the right hand side of the screen, a middle income group. So that gives you information about the flow that you're going to have to calculate. You're told that the pipelines are UPVC pipelines, a suitable N value, right? Your Manning coefficient, suitable, you must use a suitable one, and I have spoken about that. It will be N equals to 0.12. And you ask now to design a suitable pipe size for this particular pipe, from manhole 2 to manhole 3. So you identify in this network, I've labeled those manholes, and I've called it that one manhole 2 and manhole 3. Right, so we want to now design that particular pipeline. So the procedure to do is you can see that as you move along the length of the pipeline, the flow in the pipeline will increase. Right, right at the first, at the start of it, at the beginning of towards the beginning of the pipeline, it's only serving 2 or 3 or 4 properties. Right, if you look at it around that point in the pipeline, around that point, at most you'll have the flow from 4 properties occurring into the pipeline at that point. But as you come just before the manhole, immediately before the manhole, at some point over there, you're serving now. If you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right, so you have about the flow from 20 properties coming into that particular uh, portion of the pipeline. So the amount of flow in that in the pipeline just before the manhole will be for about 20 uh, properties. Now, we do not change the diameter of the pipeline between manholes. That if we want to change the diameter, then we'll add a manhole. So if I wanted to change the diameter of this pipeline at this point here, then I would add a manhole at that point. Right. So we just have a manhole, manhole 2 and manhole 3. We're not changing the diameter of the pipe. So we would have to then design this pipeline for those 20 properties that we calculated. So we're designing the pipeline for the maximum flow that would occur anywhere in that pipeline, and the maximum flow would always occur just before the manhole, right? Immediately in the short distance immediately before the manhole, that's where you would get the maximum flow in the pipeline. And this entire pipeline from manhole 2 to manhole 3 will be sized for just that maximum flow over there. Right. So to calculate that maximum flow, we're going to have to work out the number of dwelling units. Now, the number of dwelling units, again, would depend on the zoning, the town planning zoning. So you'd need some information about that. That's not given. So we're just going to assume for now that for each property we have one dwelling unit. Right, so it's one dwelling unit per property. If you have a larger property, for example, in a middle income area, or you might, or even sometime in a high income area, you might have two dwelling units because sometimes they would put up a granny flat or an outbuilding in those properties. Uh, but that information would come from the municipality and the town planners. They would tell you what that area is zoned for. From the zoning of it, you can then pick up for that. For now, we're just assuming one dwelling unit per property over here. Right? And like I told you in yesterday's lecture, one property is that rectangle that you see like that over there. So in one, you have one house being built on that one property rather. So we'll assume one dwelling unit rather. Okay, so I told you now we have 20. So we're going to design this particular pipeline for 20 uh, dwelling units. This we're not. It's not part of the solution, but this as a discussion to help you understand it. If you took the next pipeline, so for example, you have manual 3 to manual 4. Right, manual 4 when you design it, we're adding another 1, 2, 3, 4, 5, 6, 7, 8, another 10 properties. Right? So if you designed the pipeline just before manual 3 for 20 dwelling units, we would then design the pipeline from manual 3 to manual 4. That pipeline would be designed for 30 dwelling units. But actually, it's serving 30 dwelling units from where I've drawn this blue line. But if you look at the flow coming through, there's manual 1 here, right? And you're told that they are, so this is flow that's coming from another suburb. And it tells you here you have 300 low income dwelling units. So when you design this pipeline from manual 3 to manual 4, you would actually consider the flow of 30 middle income units, dwelling units, plus 300 low income dwelling units. So it will be quite a large pipeline, not quite a large, but it will have quite a large, much larger flow than this first pipeline. This first pipeline for a 150 diameter pipeline would be running almost empty. It will have a very low depth of flow in this pipeline. But from manual 3 to manual 4, you'd have it would be much fuller now, that pipeline, because you got 300 low income dwelling units plus 30, right? Not 20, it'll be 30. So it's cumulative as you're moving along the pipeline. That's the important of it. The flow is cumulative. So from manual 3 to manual 4, you have 10 additional properties. So you don't design it for just 10 properties. You got to design it for the total flow that's occurring in that pipeline. So it will be the, the 20 dwelling units before the manual 3 plus the 10 dwelling units between manual 3 and manual 4. From my past experience, I know many students make that mistake. They would have only designed manual 3 and manual 4 for 10 dwelling units. So it's not 10, it'll be 20, it'll be 10 plus the 20 before that. So it'll be 30 plus these 300 low income dwelling units that you have over here. So, so that's just for the flow. So now we have some information. We would also need the slope of the ground, because we would have to decide what slope to lay our pipe. So we will need information about these contours. And just looking at it from here, we can see that the ground level at the manual 3 is roughly around, these contours are at half a meter intervals. So you have a 12-meter contour there, and you have a 13-meter contour. So this would be about 12.5 meters at around manual 3, the ground level. That's about 12 and a half. At manual 2, you're looking roughly again at about, if that's 14 and 15, so a half a meter interval. So that will be, uh, sorry, yeah, the contours are at half a meter intervals. So if that's 14, that will be the 14 and a half contour. So that will be 14 and a half. So roughly around 14.2, 14.3 meters, somewhere around there. Right? The ground level at manual to somewhere around 14.3 meters. And you'll see that just now when we're determining the slope of the pipeline, and that will come through from there. Right? So we need the ground level at manual 2 and the ground level at manual 3. Right? So whatever the ground level, we will make a note of that. ground level at manhole 2, and ground level at manhole 3. Right? So how do we go about the calculations? Let's see. I do have the memo for that, for this particular example. So, and I just want to briefly go through this with you. Right, so let me enlarge this on the screen so you see it. So I just have to flip through between the screens. Right, so we're designing it between manhole 2 and manhole 3, and I mentioned to you that there's 20 dwelling units that we have between manhole 2 and manhole 3. So to calculate the flow, you'll see I've now, sorry, let me get my red pen out here again. So is there a query? Somebody asking a question? No, okay. Right, so we're designing the pipeline between manhole 2 and manhole 3. We note that we got 20 dwelling units, right? So 20 dwelling units. The question mentioned that it was middle income, right? If you look at the on the top here, I told you on the right hand side, we're designing it for middle income, right? So middle income there. So middle income. If we go to our CSR guidelines, right, so we will go back to those CSR guidelines, and we look at the table here. We see for middle income, so that's our area of interest on this table, table C.1, 750 liters per dwelling unit per day. Right, so we have the 750, and the per dwelling unit, we're assuming 6 people. Right, so let's come back to our memo, and you'll see that that's it over there. So 6 persons per dwelling unit and the 750 liters per day. So that's our input into our design. So we've already read off from the CSR guidelines, from those tables we have that. The population that we will serve, we now have 20 dwelling units, and we have 6 people. So 6 times 20, you can see, will be 120 people. So that's the population that we're serving in that for that particular pipeline, 120 people. If we have a population of 120 people, we can then work out our peak factor. And from that table with the peak factor, it works out to 3.5. So let's go back here and look at that, and let's confirm that it's 3.5. So you see the population that's here. And again, just notice that it's in thousands over here, right? So the numbers that you see at the bottom here are thousands. So that number 8 is 8,000 people, right? This number here, for 1.5, that's 1.5 thousand, 1,500 people, right? So in our graph, we said we have a maximum population. What was that now? Let's go back here. We said we have, sorry, we have the maximum population of 120 people. Right, so you can see that it's a very small amount in terms of this graph. So the maximum peak flow that we would have, this is 1,000 on this axis here, and that would be 3.5. Right, so that's the minimum peak factor, or put it this way, the maximum peak factor that we would use is 3.5, and the minimum peak factor that one would use would be 1.8. So our peak factor is going to vary between those two numbers over here. Right, so that's where the 3.5 has come here, because the graph doesn't proceed to less than 1,000 people. So that's where we'd have that's where that number of 3.5 has come about from. Right, so so that's where the 3.5 peak factor came. The average daily flow, right, you can see the abbreviation we're using, average daily flow, would then equal to the number of dwelling units that we have. Okay, let me just so again remove all that extra writing over there. Right, so the average daily flow would be this. We have um, 20 dwelling units. So we have this 20 dwellings, and each dwelling unit uses 750 liters per day. So 20 times 750, and then that's per day, the total amount you can see per day. We want our average daily flow in liters per second, and there are 86,400 liters per second in a day, in one day. So we have so many seconds. So that's why we're dividing there, and then we end up with this 0.174 liters per second. That's our average daily flow. We then multiply it by the peak factor, and we then get 0.6 liters per second, because we're multiplying that 0.174 by that 3.5. So that's why you get a significant increase. It's 3.5 times larger. And we would then increase that number of 0.168 by 15% to allow for stormwater reticulation. So our peak wet weather flow, right? So that's why we say PWF. That peak wet weather flow would be 0.699 or roughly zero point 0.7 liters per second. Right? So that's the unit is not shown here, but that's what it would be, liters per second. Right? That we would have that. So that's what we after, and that's what we would design our pipelines for. That is our design flow, zero point 0.7 liters per second. Now, you'll see here that that flow of 0.67 liters per second is being converted to liters per minute. So there are 60 seconds in a minute. Right? So we will multiply that by 60 and we get this value. Now, this is the only reason it's being done in this particular tutorial is because we're going to need to guess a pipe size. And to give you some guidance for guessing a pipe size, I have supplied you, and you'll find this again on Moodle, with this nomograph, right? It's called a nomograph, and it helps you to select a pipe size. You'll see at the bottom here, you've got the slope of the pipeline. On the right-hand side, you have pipe diameter sizes, and on the left-hand side, you have various discharges, right, or the flow in the pipeline, and it's given in liters per minute. That LPM here stands for liters per minute. So that's the reason in the tutorial we converted to this liters per minute. I have actually recently come across in one of the catalogs, a South African catalog, where we have the same nomograph but given in liters per second, which I will upload for you in Moodle. So if you have the liters per second one, then you don't need to convert the flow to liter per minute. Right? But this one is because this nomograph is in liters per minute. That's the reason we converted. Okay, and you also need to note it's a logarithmic scale. If you read the numbers, so for example, once you reach 1,000, then it's not 1,200, it's actually 1,000, 2,000, 4,000, 6,000. When you reach 10,000, the next number, that 2 stands for 20,000, 40,000, 60,000. Right? That's the way you read a logarithmic graph. So the vertical scale is logarithmic, the horizontal scale also partially, no, the horizontal scale is not logarithmic. No, it's not logarithmic. Right. So we now okay, we calculated okay, our peak flow, and then we come to this graph over here, and we then will select a particular pipe size. But in the tutorial, before that, we need the slope of the pipeline, because when we look at this nomograph, you can see at the bottom, the bottom axis over here, that's that bottom axis. You have to know what's the slope of your pipeline. So for us to determine is to get some idea of what slope we can lay the pipeline at, we would need the natural slope of the ground. Now, again, this is something I found, I didn't realize it initially, but I found many students actually make a mistake when it comes to the slope of the pipeline. I just want to talk about that for briefly for a minute or so. If your natural ground, for example, is sloping like that, to say that's your natural ground level like that. Right? Now, if you starting off, you have a manhole at that point like that. So I'm just showing the manhole with a vertical line like that. Okay, I'm going to draw it deeper. It's just for illustration purposes. You have a manhole at that point over there, and you then want to lay a pipeline to a second manhole somewhere further down. Right? Now, and you usually, let's say this might be at minimum cover over here. So let's say if it was in a road and we had 1.4 meter deep, if this manhole was 1.4 meter deep, and if we come into a second manhole over here, and we want our pipeline to all the time be 1.4 meters deep, that's the cover we want. Right? We spoke about the minimum cover requirements. Now, if we are working with a minimum of 1.4 meter cover, then it means our pipeline that we lay will lay it parallel to the ground. Right? Because that's 1.4 meters deep. At that point, the manhole, we dug it, and then this side further down, we're going to dig the manhole at 1.4 meters deep. We're assuming the ground is straight, falling at a constant slope like that. So if we laid our pipeline at the same slope as the ground, then we know we would achieve the 1.4 meters cover to our pipeline like that. Right? We would then achieve that 1.4 meters like that. But uh, it's not that's not always achievable, right? It commonly happens. So, for example, that when you come to, for example, let me just delete this over here. Let's say, for argument's sake, that if we got the 1.4 meter depth at this point here, and we laid the pipeline like that, but let's say the ground slope is relatively flat, and we got to lay our pipeline to a certain minimum slope. So to achieve the minimum slope in the pipeline, we may not necessarily be moving parallel to the ground. So it might happen that sometime your pipeline is actually getting deeper and deeper as you're going like that. So when you come to the next manhole, uh, you may have started off here with 1.4 meters, right? But you cannot keep up with that 1.4 meters parallel to the ground because maybe you need a minimum slope for your pipeline. If you're going to lay it that you have 1.4 meters on the left-hand side, it would mean that your pipeline would be too flat, right? And you won't achieve that zero point 0.7 meters per second velocity. So to achieve the minimum velocity, you need to lay the pipeline steeper. So this pipeline does not have to be parallel to the ground level. Just bear that in mind. That's the whole crux of it, what I'm getting to. Right? It doesn't necessarily have to be parallel to the ground, to that the slope of the ground. Sometimes the ground is, I'm just drawing again, the ground is very steep like that, right? And for whatever reason, you may be joining into another pipeline, you may be coming across, you might be sitting with quite a deep manhole there. But you don't need to lay your pipeline after that at such a steep slope. So sometimes you might actually be getting shallower and shallower and shallower till you come to your manhole there. And this manhole here may still have the 1.4 meter cover to that if it's in a road, whereas this manhole here might have been at 3 meters deep like that when you started off. So here you can see again the pipeline is not parallel to the ground level. It's actually getting shallower and shallower, but you're still achieving your minimum cover of 1.4 meters. Right? In the top scenario, you're getting deeper and deeper. Right? You're going much deeper than the 1.4 meter, but you need to lay that pipeline at that minimum slope. At this in the bottom diagram, that would still be at your minimum slope, and you're still getting 0.7 meters per second. Right, so hopefully that's clarified that whole issue. Now, I think that the confusion comes about because in this particular tutorial, I'm working with the ground levels, the contours that we have, right, in this particular one. So I told you in this normal graph, we need to work out the slope of it. Let's go back to the tutorial cell solution, and you see here, uh, I mentioned to you about the slope of the ground. That we need to work out what's the fall of the ground, and to work out that slope, you need also the length between those manholes. So let's go back to the tutorial question. We need the slope of the ground. If you look at it, the fall of the ground level between those two manholes. Let me just clear out the clutter from this drawing here so that the relevant information stands out. Uh, right, so we want the fall of the ground. If you look at here, we're looking at about 13.5 meters, right? So not 13.5, we said about 12.5 meter. That's the ground level there. Right? 12.5 meters, the ground level there. At manhole 2, we said we're looking at about maybe 14 point, this thing. Roughly, I got a feeling in this, I just want to check it, okay. Okay, it doesn't matter. 14, it's about roughly, we said 14.3 meters, something like that over here, right? 14.3 meters around there. So the difference in ground levels from 12.5 to 13.5. So it's where is it? 12.5, yeah, that's correct. And
Have you done about water?
sorry, is that
Yeah, Fatima just phoned to say they got water. Yeah, that part of. That part got water.
Sorry, can one of you just mute your mics, please? I can hear somebody talking about water, and I also don't have water at home, so I'm happy to hear maybe the water is being connected. Uh, but I could hear someone in the background talking about water. Anyway, coming back to this question, so we need the difference in ground levels over here because that gives us an idea of the fall of the ground. Right over there, and that's the information is used in this particular question for the slope of the pipeline also. So if you look at it from 12.5 to about somewhere around 14.3, I know I haven't used the exact values in the solution. So 13.5, that will give us about 1 meter to 13 and a half, and then about another that to 14.3, so it'll be about another 1.8 meters or something like that. I think I've used 1.5, so I'm working to roughly about 14.4 meters or something over here like that, right? So maybe instead of 14.3, if we work with 14.4 meters over here. So there's roughly about 1.5 meters of fall in the ground level between manhole 2 and manhole 3. We also need the distance between manhole 2 and manhole 3. And to get that distance, okay, I'm just going to zoom out. How would you get that distance for this particular question? This that distance you would necessarily need this drawing to be to a certain scale, and then you can measure it off from there. You'll notice here that at the bottom right hand corner of that contour map, you're given the scale of 1:2000. You've all done drawing and drawing 3. You'll know how to use your scale rule. So you take your scale rule, uh, go to the 1:2000 scale, and then measure that distance from manhole 2 to manhole 3. Right, so that's how you determine the distance, and this just the difference in ground slope, you would get it from the difference in the contours over there, right? So you, for using your contours, you'd have to interpolate whatever and then work out the difference in ground levels. This coming back to the scale rule again. If your scale rule says 1:20, you can still use it. Right? If your scale rule said 1:20, you whatever you would measure from the 1:20, you would then multiply it by 100 times. Right? Because 20 times 10 would give you 200, 20 times 100 would give you 1:2000. So if you don't have a 1:2000 scale, but you have a 1:20 scale, which is a common scale, you can still use the 1:20 scale and measure that distance between those manholes. That was just by the way. You should know that already from your drawing module. Right. So we then have the distance. So let's come back to our tutorial system. Yeah. So when we, from the scale rule, when we measure those distances, we get the length is 88 meters. And I told you the difference in between the ground levels using those contours was 1.9 meters. So the slope of it will be equal to the fall divided by the length. And that would, you get a value of 0.022. Right. But if you notice that normally when we talk of the slope of the ground, we don't give it in this format. That's not the common format. We would normally give it in the format of 1 something. Right? Now, what does that 1 something means? If I told you that the slope of the ground is 1 in 10, that's if I told you that the slope of the ground is 1:10, that's I'm just giving an example. So if I told you that the slope is 1:10, what does that mean, 1:10? What it means is that for every 10 meters that horizontal, right, for every 10-meter horizontal, uh, the ground rises by 1 meter. So that's 1 meter. Right? So 1 meter rise in 10 meters. So then that's okay, let me draw it in a different color. The blue line is actually the sloping line. Right? So that's what we're specifying it, the sloping line. So this blue line here that I'm now drawing is at 1:10. That's the slope of it. 1 meter vertical and 10-meter horizontal. So that's your vertical versus your horizontal. We normally will specify a slope like that. So this 0.022 is equivalent to a 1:46 slope like that, right? Why am I looking at the slope like that, 1:46? If you recall, when you go back to the CSR guidelines, you see it here, minimum gradients, they specified as 1:something like that, right? You can see 1:something like that. So that's how we normally specify gradients of pipelines. And we will also put this information on our long section, and I'll discuss that long section in the next lecture. Right, so that's why we need it in that particular format, 1:something, and that's why we've converted it like that. So we now have the slope of the pipeline. We have so if we got the slope of the pipeline and we got our peak flow, right? So our peak flow there. So we got the peak flow. We actually then converted that peak flow to liters per minute. So we have those two quantities, the peak flow per minute, and we have the slope, 1:46, roughly about 1:50. When we want to use our nomograph, we can then go back to this nomograph, and now we will look at it over here. Now, I know this particular nomograph here is not so clear. In Moodle, you'll find a much clearer one. Actually, this one is not so bad. Okay. Okay, the one in the tutorial solution is not so clear, but the one that I'm using here on the screen is much clearer. Just to show you, the one in the memo that you have here at the bottom here. See, you notice this one, you cannot read the pipe diameter so clearly. But I've got a separate now file just by itself. That's this one, and here you can read it clearly. So coming to this nomograph, just to show you how you read it, you see here that you've got various slopes at the bottom axis, 1 in 10, 1 in 30, 1 in 60. We are 1 in 50, so that's 1 in 30, that's 1 in 40, 1 in 50. So that's the, we have drawn in blue. That's the vertical axis, the vertical line on our graph. And then from our solution in the tutorial, sorry, let me just go back down. Where was it now? Tutorial one, this is the one that we worked out to 42 liters per minute. Again, I just want to delete all this clutter here, just so we can see the relevant information more clearly from this, what we're actually working with here for that nomograph. Right? So these are the two important figures that we're looking at. The slope, we said roughly around 1 in 50, and the our peak wet flow, or peak flow, is roughly about 42 liters per second. Right? So when we go to this nomograph, that was the 1 in 50 slope, and we said roughly about what was it, 40? I'm getting old, I'm forgetting quickly. I think it was roughly about 42 liters per second. Right, so 42 liters per second. On the vertical graph, we're going to try and find 42 liters per second. We're starting, so not 42 liters per second, sorry, 42 liters per minute. Right. We're starting off with 100, so it's somewhere below this point over here. So even if we worked with 100 liters per minute, if we came across and intersected here, you'll see that we can intersect that line at that point, roughly around that point over there. Right, somewhere at that point over there. Now, if we used a 100 diameter pipe, right, if we, so you can see here that a 100 diameter pipe can work for that particular flow. But we're not going to use a 100 diameter pipe because our minimum pipe size is 150. So that's what we will target over here. Now, if we're using a 150 diameter pipe, what this nomograph tells us at a slope of 1 in 50, for a 1 in 50 diameter pipe, we see where it intersects that pipeline. So it's going to intersect that pipeline around that point over there. So I will now get rid of this. Remember, because we're not working with full bore flow, it's going to be partially full. And if we look now at this nomograph, so we came, oh, sorry, where did I delete this bottom one? That's our 1 in 50 slope over here. At that point, we had the 1 in 50. That 1 in 50 is at that point, just to show you. We then come up here, and until we intersect this 150 diameter pipe. At that 150 diameter pipe, if we move across here like that, what it tells us is that we can then easily discharge a bit over 1,000 liter per minute. We only have 42 liters per minute, so a 150 diameter pipe is far, far, far more in excess of what we need, but it is the minimum, so we're happy with that size. Right? This is about roughly maybe about 1,200 liters per minute or something like that. 1,100 liters per minute, somewhere around that kind of flow we can achieve in that pipe at that particular slope, at the slope of 1 in 50. And then what's nice about this nomograph, it also gives us some idea about, we also have to worry about minimum velocities. So the lines that go across in that direction, like that, the lines that are in that direction, those are the velocity lines. So they're written at the bottom and the top. So if you look at where our blue dot is for the 1 in 50 pipe at a slope of 1 in 50, we see that we can achieve roughly about 1.2 meters per second. Right? That will be the velocity. So that's the velocity, full bore velocity that we can, actually not the full bore velocity, that's the actual velocity that we can achieve in that pipeline. Right? And our full bore velocity will be usually larger than that amount over there. So we're happy with that. We over the 0.7 meters per second. That same 1.2, if you read it across from that point, you'll see if you were to just continue reading those lines. So from 1.4 upwards, it's written on the top, and from 1.2 below, you see it on the lines below there. Right? So this is what helps us to select. So I know for sure, looking at this nomograph, a 150 diameter pipeline is what I need. It's more than adequate for me. Right? Uh, uh, Even a 100 millimeter pipeline will work. If I, just to, for argument's sake, just to if I had to look at the 1 in 50 that sorry, if I had to look at a 100 millimeter pipe, it would intersect at that point. My 1 in 50 slope intersects the 100 millimeter pipeline at that point. When I come across here, I can already see I'm about 400 liters per minute, and that's more than enough for my 42 liters per minute. So it's going to work quite easily. From a flow velocity point of view, between 0.8 and 1 meter, in fact, slightly above 0.9 meters per second. So even the velocity is acceptable in this particular in a 100 diameter pipe. So a 100 diameter pipe will work. The nomograph tells me to work, but it's not the minimum according to our guidelines. For the guidelines say for the municipal sewer, use a minimum of 150 diameter. So that's what we will use. Let's go back to our solution. So we then come back to the tutorial solution, and based on that nomograph, so you can see I've included this nomograph, and I've then put a discussion to tell you basically what I've explained to you now. You'll find all of this discussion here. Just bear in mind this nomograph is based on n value of 0.013, whereas our guidelines say we must use a value of 0.012. So there is a slight adjustment for that. You can see the adjustment being made for that factor, but it's not so critical. This is our preliminary selection of a pipeline. We're still going to do calculations to check it properly, and we can see that the 150 diameter pipeline works well with us. I've explained that to you. So now we decided that for that 1 in 46 slope, and for that flow of 42 liters per minute, our peak flow, we now we're using a 150 millimeter diameter pipe, and now it looks like I don't know why my computer is actually dimmed out. Just bear with me, please give me a minute. I just want to see what's happened. Yeah, it's not. Oh, one of my kids at some point in the morning unplugged my power supply. Just give me a few seconds while I plug in my power supply again before my computer switches off. All right. Hopefully that should resolve things. Yeah. Okay, so my apologies for that. I just had to plug in the power supply to my laptop, but as it would have switched off. Right, so you can see again, I've spoken about all what's over here. Now, according to the nomograph and according to the guidelines, 150, but a UPVC pipeline does not come in an internal diameter of 150. It will be 160. Right? So that's from a practical point of view. Our UPVC pipelines, the manufacturers make them in a 160 millimeter diameter. Right? So we will then work with a 160 diameter pipe. And now we will do the checks. We want to work out what's the actual depth of flow in our pipeline. We want to work out what's the actual velocity of flow in our pipeline. What's the full bore velocity flow in our pipeline. We want to do all those checks over there. Right? We're going to be using the Manning equation for our sewer reticulation design. So we use Manning's equation. Right? In Manning's equation, we're going to be using n. Okay, I see in the tutorial here I've used 0.013. Maybe in the question there did I specify? I just said use an appropriate n value. I just want to check here. In this particular example, or we just said use a suitable value for n. Okay, so in this particular one, I've used a Manning's equation of 0.013. I should have more correctly, I should have actually used 0.012 here. The pipe slope, that 1 in 46, right? If you convert it to this in our equations, our equations don't allow for input of 1 in 46. Our Manning's equation, right? We got to put the slope in this particular format. So you have to 1 divided by 46. That's how we will put the slope of it. So you get that number there, and that's our pipe diameter size that we have there. We then use the Manning's equation, and you can see the full bore flow. That's the Q, the capital Q. Right? That's your full bore flow. Just note that it's capital Q, right? Small q is generally the actual flow in the pipeline. Right? Capital Q, we reserve that for full bore flow. Similar with velocity, capital V will be the full bore velocity. Small v will be the actual velocity. So you see here the Manning's equations. So we have for the velocity and for the q there. It's easy to convert from the one to the other. It's just you're using your continuity equation. Your q equals to VA. So you're just substituting from the one into the other equation, and that's how you would get it. Right. So the Q over here, uh, the full bore for 150 diameter pipe. So for the D, we would then so it's 160 diameter pipe. For the D, we're going to substitute 160. That's your N, your Manning's equation, and that's the slope that I spoke about. So that's where you can't put in 1 inch to 46 over here. You'll put in the one in what we said the 0. Not 1 in. You just substitute that number 0.022, 1 divided by that 46. That was the slope we worked out earlier. Just to go back here, just to show you, that's the value of the slope we substituted from what we obtained over there, and then we converted that into a 1 in something format over here. Right? So that's what we're going to substitute in these equations. We then see that we get a full bore velocity of 26.59 liters per second and a full bore velocity of 1.322. This is greater than the 0.7. That is greater than the 0.7. So we're happy with that, right? Greater than 0.7. So we're fine with that value over there. Now, our actual flow that we worked out was, if we go back in liters per second, let's go back to our calculations over here. When we worked out the actual flow, we worked out was our peak weather flow was roughly about 0.7 liters per second, something like that, somewhere around there, right? That was the actual flow. And our full bore uh, our full bore flow we worked out over here was 26.59 liters per second. So we will then divide that actual one, that the small value that we calculated there, about roughly about 0.7 liters per second, by this 26.59, and we'll end up with this value, here, this ratio that we gave here of 0.026 over here. Right? Now, why are we doing this? Why is this calculation being done? This is where that second set of notes that I've given you, that it explains to you what the table and the graph that I'm going to show you just now. That in this particular, you can read it, you can study it, you should be able to derive these equations in a test or exam situation. You could be asked some theory. So this is all part of the theory. If you study this whole set of notes, you'll notice that we come here, just to show you, to this Q over Q. Right, but you first got to do the previous calculations before you come to this. This is that same ratio, Q over Q, and you can then, in this equation, solve for theta. Right. And once you've got theta, you can then go back and substitute into these equations here for V over V. Right. So so if you know what theta is, you can substitute for this, and you then calculate that ratio of V over V. Now we know what the capital V is, actually the full bore velocity. So we would then be able to solve for the small v, which is the actual velocity in the pipeline. Similarly, for the depth of flow, if you go back here, you'll see the ratio d over d. Small d is the actual depth of flow, right? So that with the hatch, the depth of this hatch, so what I'm that depth there, and capital D is the diameter of the pipeline. So if you know what theta is, you can then, you know what this ratio D over D equals to, you can work it out. And you know what the capital D is, that's 160, that's our pipe diameter. So we would then be able to work out the small d, and we know what the depth of flow is in our pipeline. Right, that's what we want. So these are the actual equations. If you are using, for example, a spreadsheet, or you wrote a computer program, then you would require these equations here, which I've derived for you. And we will then, we'll see how we'll use these equations also just now. Right, so coming back to our tutorial solution, we now have this Q over Q ratio. So you can either use those equations, or those same equations, so clear out the clutter for me, those same equations are represented in this table here that you see, the values. So you can either read out the values from this table, or you could use the, sorry, where's that? There's a graph. Now, why is it not drawing? Bear with me. I think it takes a while for the PDF file to read that. I'm just waiting for So there is supposed to be a graph here after this. Okay, so I don't know, for some reason it's not opening it there. I'll just show you it, just to show you something. No, that's not what I'm looking for. Oh no, my Microsoft Edge has hung a bit. It takes, I don't know why it stalls for a few seconds, so you just have to bear with me. I need to go back to that normal graph. Try. Okay, coming back to this over here. I had this normal graph here. No, so okay, yeah, the same. Okay, okay, it's in this particular. Sorry, and this I got confused. I confused myself for a while. In the same document here, you'll come across. You see, there's a table here. So what these equations represent is summarized in this particular table. So you can either use that table in graphic format. That's what it's represented over here, right? That you see in this
Sir,
particular. Yes.
I can't see your screen.
Uh, is there anybody else having that problem?
Sir, it's back now.
Is it back now? Okay, thanks for that. Right. So when we look, if you look at this graph here, and I'll spend again a minute or two just to explain something about this graph. It's quite informative when you look at this graph. You'll see that there are two curves in this graph here. Right? The one is QP over, I don't know, what's that, QF or something. I don't know, something, whatever that is not so clear over there. Let me try and enlarge that. But anyway, what it's the first one is the small q over the capital Q. Right? That's what in essence from the notes that I got over here. So you can just picture it, just imagine it as a small q here over capital Q, like that. And the second curve here is giving you the small v over the capital V, like that over there, right? And that's what you're reading out at the bottom here, the values for those ratios that you have over here. Now, if you look at the flow in the pipeline, the small q over the capital Q, the ratio, in others, of the actual flow to the full bore flow over here, against, and on the left hand side axis, or the vertical axis, is giving you the D over the D. So again, I know it's okay. I've extracted this from another document, but in your relative to the notes that I got in the terminology we use, it's actually small d over full D, right? The actual depth of flow over the diameter of pipe over here. So when we read this and you're looking at this, you can see obviously when there's no flow, then the actual depth will be 0. Right, when this can only be this ratio can only be 0 when the small q is 0, so there's no flow like that. When you come to about the so when the flow in the when the depth of flow in the pipeline is half, when the pipe is flowing half full, you then get half the full bore flow in the pipeline. You can get half the full bore flow in the pipeline. Now, what's interesting, you'll notice that as we move along, that Q over Q, that's the 1, the axis for 1. So Q over Q equals to 1. And you see it actually goes above 1.1. So you can actually achieve more flow in the pipeline when it's not full than when it's full. Do you see that happening? See, 1 over 1 represents the pipe is flowing full, right, to the full depth. But when the pipe is flowing at around 95%, somewhere around 90 to 95% full there, so somewhere around there, if you look at it, around 90 to 90, say 90%, if you approximate it, say around 90% full flow, when it's about 90% full, then the Q value, the actual compared to the full bore flow, the Q value is larger than the actual full bore flow. If you come down here, you see you're actually a bit larger. You're about maybe, I don't know, maybe 10% or 5% more flow in the pipeline. So it's about, if that's 1.1 and this is 1, and maybe 1.04 or something like that, around there, 1.05 actually, yeah, maybe about 1.05. So you get about 5% more flow in the pipeline, right? When it's flowing at somewhere around 90% to 95% full. right, and not full. When it comes back to full, then you see the amount of flow decreases it comes back to the full bore velocity there. And the similar situation with the velocity in the pipeline. Right? The maximum velocity that you can get the maximum velocity of flow is when the pipeline is flowing 80% full, right? Because you got less friction from the sides. Right. That's what, in essence. So that's what those formulas above. If we plotted it in the form of the graph, they tell us. So at about 80%, you achieve the maximum velocity in the pipeline, whereas when you come back to full bore flow, then you would be back to your full bore velocity. Right. Uh, to achieve half the full bore velocity in the pipeline, if you look at it, you would only need about the pipe would only need to be full to about 0.15 of the depth. Right, so maybe only about 15% of the depth in the pipe, you would already achieve about 50% of the full bore velocity. Right, so if you want to on your own, look at this graph, and it's quite informative from that point of view. That was just I told you by the way to some information you gauge from this graph. We need to still check our design, so we're going to come back to this. Let's see what we had over here. Right, this is the table that we have here, and this is the graph. And I'll now come back. Okay, looking at this particular graph, what it's telling you here at the bottom, the numbers in italics, right? The numbers in italics, they call it KP. And if you look at the bottom here, KP, that's to do with the velocity, right? So the number in italics is the velocity, and the number that's not in italics, that's your flow, Q values, right? So italics is V, the V values, and the normal font is your Q values. Now, how you read this table, you see here on the top right-hand corner, you got D over D, and again, it's actually we work with it the other way around. We work with small d over capital D. That this table was extracted from a book, and they use different symbols. So this changed that to small d over capital D in this particular table here. Otherwise, you can use the equations. And so the value down here, this is giving you the d over d. So it's for set values, and it's in increments of 0.1, right? Not 0.1, 0.2, 0.3, 0.4. And if you had, for example, a d over d of 0.24, for example, then you'd come across here, right? So you then look down here, which if I, okay, let me just do it in the case of an example. So if I had, for argument's sake, d over capital D equal to 0.24, right? So 0.24. Let me write that 2 better there. So if I had D over D of 0.24, then I see over here D over D, I get 0.2. Right. And then to get the second part of it, this decimal, the 0.04, I come across here and I look at that. So this table over here, so that's now the 0.04. So 0.24, where these two intersect. So I then come across like that from there, and I come down like that. So that's the 0.24. So these two set of values here that I have, that I put in that box over here. That's so let me get rid of those lines there like that. So these two values that I have in the box, these two values here represent R for D, D over D equal to 0.24. Right, so that's the box that I would read off. Now the top value, that's the normal font. That tells me in this particular one for that D for this D over D equal to 0.24, it tells me that my small q over capital Q, small q over capital Q is equal to 0.1263, right? That's what it tells me. Now I know what the capital Q is. I've worked out capital Q. Right, let's go back. Okay, sorry, I'm the nomograph one. Right, so I know what the capital Q is. If I go back to my the solution, where is that solution? Let me just open that file again. If I go back to the solution here, let's go up here. I did work out my capital Q, and that's the value of capital Q. So I can then substitute for the capital Q there, and I will then get the value for the small q in that. So let me go back to the right diagram of it. So I can then work out what my small q is, and that will give me the actual value. So if I had 26 liters per second, if I multiply it by that 0.1263, then that will give me the actual flow in the pipeline at that particular slope that I had over there. Right, and I think I worked with a slope of 1 in 46. That's what we got over there. So for 1 in 46 slope in the pipeline, that will be uh, and for what was it? It's zero point 0.7 liters per second. Then the actual flow, the full bore flow, sorry, was quite high, and that's the actual flow over there that we get over here. So this is what it's telling me for that for the depth of for d over d of 0.24. Sorry, yeah, for d over d of 0.24 in a pipeline, that my actual flow will be if the full bore Q was 26 liters per second, or whatever that was, then it will be Q times the capital Q times that. I can now work out. So simply put, I can work out what small q is. In the same manner, the italic value over there, it's telling me that my small v over my capital V is equal to 0.6844. I haven't written that nicely, so let me just write that again properly. Small v over big V is equal to 0.6844 like that, right? So I know what my capital V is. That's my full bore velocity. I used my Manning equation and I calculated that. I can then calculate what my small v is. Right. So from this table, I can work out what my small q is and my small v is. Now I'm just showing you the use of this table. Right. It's not the way we're going to use it in the solution for what we have, because we already have the small q over here. Right. What we after we're going to use it in the reverse of what I showed you now. What I showed you now was to explain to you the normal font and the italic font over here, and to how to read the d over d on this graph here. That was what I was my main purpose now in the explanation was to do that. Right. Now let's come back to our solution. Right, to our tutorial solution. So I'm going to delete all of this from here, and you'll see how we're going to use this table now for our tutorial solution. So let's get rid of all this information from here. Right. Uh, Now we have, so let me go back to the solution. Just bear with me, please. I keep swapping screens here. Right. Now we had this value. We worked it out just now, and I showed you that we know what the small q is, and we know what our big Q is. Right. So we know that. We don't need to find that small q over big Q from this particular table. We already starting off with that information. So coming to this over here, we have this q over q of 0.026. So what we do is we come into this table here and we look for the normal font where we can find a 0.026 or something closest to that value. So then look here and I see I got 0.0048. That's far away. I'm getting a bit warmer here a little. I see 0.0 209. That's quite close over there. Maybe if I go the next one, 0.025, and that roughly rounds off to about 0.026. If you notice where my cursor is circling, right? So when I look at that value there, I'm in that ballpark figure there. That looks like 0.026 over here. Right. So this is my Q over Q ratio, which I have from my calculations that I've done over here. So that's the one that I want to read over here. So I know that's the box that I want over here. So this is the box. I will then highlight this box here. So that's where I am in over here in this table. And now using this, I can calculate what my D over D is, right? Because I can then go up like this and I can come across just remember, on the solid line, not the italic, so I don't come across on the bottom like that. I'm coming across the top. So this, what I've done now, tells me that my small d over my capital D is equal to, small d over capital D is equal to 0. Let me see if any one of you can guess what's that. 0.11. Right. That's the first decimal on this vertical column, the first decimal, and the second decimal is on the horizontal ladder. Right. So the D over D ratio, the first decimal is down here, and the second decimal is down on that, as I'm showing you there. Right. So that's where I get my two decimals for the D over D ratio ladder. Right. So I know my D over D is that. That would then imply that, and I know what my capital D is. I'm working with a 160 diameter pipe, so it tells me that my D, the actual depth of flow, would equal to 0.11 times the 160, because I'm working with a 160 diameter pipe, and that will then give me the actual depth of flow in my pipeline, and that's worked out down here. Uh, Okay, now it's cut off. You can see the actual depth of flow is 17.6 millimeters over here. That's what it would actually work out to. The 0.11 times the 160 millimeter, 17. So that 0.11 that I've got here in this value here, that's where it's come from over here. So that's how I picked up that value of that 0.11. That's, you see it in those calculations there. Now, I also want to know. I got the Q over Q. I want to know the velocity. What's the actual velocity? So the italic value that I see there in that box for Q over Q, I had that 0.026, and that's how I selected that box. And I see below that 0.0255 or 0.026, below that, the italic value is 0.4260. So that tells me that my small q over my capital Q for my pipeline is uh, 0.4 0.4260, and then I can then work out my small q, what is equal to. My capital Q is 160. Sorry, my capital Q is not 160. The capital Q is what I worked out here, 26.59. So let me just delete all this here. So I based my Q over Q value on that, and from that I came and read this box here, and then from that box I was then able to read the D over D ladder. And now I read my V over V. Sorry, what have I done here now? Okay, sorry, I had Q over Q 4. My apologies, I've written this wrong. Yeah, that's what I was just wondering. Sorry, I'm sorry about this. It's V over V, right? So no one corrected me on that. It's a small V over capital V, and then I can then see my small v is equal to this over here. Right. So the small v over the capital V is 0.426 over here. So that's what I've read. Let me draw a line here, so then you'll see it. I've read that value there, 0.0436. So that's that value there that I substituted, and that's the V over V. I know what my capital V is. Right? The capital V is the 1.322. So that capital V, that's what I'm going to substitute in this equation, and I can then work out what my small v is, and I would then work out the actual velocity in the pipeline. Right? So the only unknown here is the small v on the numerator. So I can then work out what the small v is, and that's done in this calculations below. You'll see it. You can see that same 0.4260. That was the v over v ratio I read over here from this graph, and I then worked out what my actual the small v is. I could then work out what the small v is, and I worked out that its v is equal to 0.563. Right. Now this is less than the zero point 0.7 minimum velocity. Uh, right. This is less than the. Sorry, this I haven't circled it nicely there. It looks like v. This is 0.426 times v. So the small v is actually that value there. Right? You can see the equal to sign over there. So my actual velocity is 0.563. It's less than the zero point 0.7, but the design guidelines, that's what I told you earlier, it's the full bore velocity that must be larger than 0.7. So the full bore velocity we worked out was 1.322. Right, so that's fine from a design point of view. But it's just telling me that the actual, so I can, so what it tells me that during normal flow, I will get some sedimentation occurring, but the pipe will be self-cleaning. Right, occasionally I could get a blockage in that pipeline also, and that's something that I would need to live with, or I would tell the municipality that, look, from time to time, you will possibly get a blockage in that. And it's quite common in the first line where you're starting off from the first manual when you're moving down, because the flows are very little, you have very small flows, so it's quite common to get blockages in those particular lines. But the actual V you can see is 1.32, is greater than 0.7, so that's okay. Right, so this is where I do the checks in my design to see that yes, that 160 diameter pipeline actually works like that. Right. So you have it all here in the solution. I've just explained it to you, how all these values are obtained here in this tutorial solution, and you've got all of these answers over here. Right, so you can go through it, study it in detail. It looks simple when I explain it, but you have to actually work with yourself. Then only you really fully grasp it. I noticed there's a little bit that's cut out here. So what I'll do is, it's a matcad file. And it's printed to PDF, so something's I don't know why. I'll have a relook at that and see this, try and ensure that I can get that next line also printed over there. It's usually to do with the selection of the printer. It means the print margins were not set properly, so that's why that little bit, that one line cut off there. So I will reprint the solution and post it for you on Moodle again. Right. So this is the actual design of a sewer reticulation pipeline. We see that yes, our 160 pipeline will work. The flow is not an issue, the slope is not an issue, and the velocity also is not an issue. The depth of flow, yes, it is. We'll only have in the 160 millimeter diameter pipe, the maximum flow depth will only be about 18 millimeters. So that's a very, very shallow flow in the pipeline. But because it's at the start of the line, we just have, there's nothing else we can do. Right, so that's what we will have. So the 160 diameter pipeline does work in this particular case over here. Right, so I've gone through the full example to show you how we actually design a sewer pipe, and we've gone through the whole thing. Now, yes, one more thing. Coming back to this whole, not this nomogram here, this calculations here, this entire table, right, where we read those values from and we used, is represented in this graph. So if you wanted to, for example, you could have actually read it off from this graph, but you'll find that it's not so easy to use this graph. It's much easier and much more accurate to use the table. Right, so to come back to our particular example, let's go back here just to show you. Uh, we were here. We're starting off with a Q over Q. That you're starting off with a Q over Q of 0.026. So if you wanted to use that this graph over here, then you would then have to 0.026. Right. So on this somewhere you'll have to try and figure out where 0.026. That's 0.01. So I don't know, 0.02, maybe somewhere there, and then you would come up here and read off from this graph here what's your the sorry, not even that. I'm again working in reverse order. On this graph here, on this the top line, you would have to find where the 0.026 occurs. So it's somewhere around at that point over here, somewhere around that point over there. That on the graph. That's where the ratio of small q over capital Q is 0.02. So to read off somewhere over there on that graph. And then from that, you can then work out what your D over D is. You come across here. Yeah, and you can see there roughly about one. We said about 18 millimeters. This is 10 millimeters, or 0.1. So that would be about, okay, not 10 millimeters. This is 10%, roughly around there. So around 160, somewhere around there, right? For for a 160 diameter pipe, about 10 millimeter will be about 16 millimeters, somewhere around there. And we said we had about 18 millimeters when we did the calcs, right? So somewhere around there. So when we come across to the left-hand side, that would give us our D over D. And if we move across to the right-hand side like that, where it intersects that V over V, and then we come down, that would give us roughly about our V over V. Like that. So if you're using the graph, and you can see that you cannot work so accurately if you use this graph. It's much more accurate. And if you come down this graph, we had about 0.463 or something like that in our previous one when we read that value of something like that was the V over V, 42643, roughly about 0.43 it was over there. Right? So we can see roughly when we come down in the graph also, we somewhere in that sort of region over there. Right, so that's what you can, it's possible to use this, but it's much more accurate to use the table values than to use this particular graph that we have here. Okay, with that, that brings us to the end of the design of that pipeline. Now, well, that's only one of those many pipelines that we've designed, right? So in this in this network, we would then now proceed and now to repeat the whole process for the pipeline between manual 3 and manual 4. Again, repeat the whole process for between manual 4 and the next manual, and proceed later to the next manual. So for each and every pipeline, we would have to do that, and it's best done if you're doing it manually. You would normally set up a spreadsheet in Excel, and you could then you do it in Excel. It would be much quicker that way. Or the norm out in industry in today's times is we use software, and software that actually works together with your CAD programs. So this network would be drawn out in your CAD program, and then the additional software, the add-on package, you would then add on your design information, and you could then be able to design these pipelines. We're still not complete with the design. We just decided on a pipe size. We still need to draw a long section. Right, we still need to draw a long section for that pipeline, because as we've done it, the contractor cannot build it. He doesn't know. He doesn't have sufficient information to actually lay that pipeline. And so that information will be provided on the long section, and I'll cover the long section design in the next lecture. Okay, it's already 11:58. I'll end the lecture at this point. Any queries? Let me end the recording. Let me go here. Stop recording. Okay, stop the